Hi, I'm Daniel Cisneros, and today I'm going to be presenting public electric vehicle charging access for the state of New Jersey. This is going to be a spatial statistics analysis by census tract. Before we get into our data, I want to explain why this topic matters. New Jersey has a goal, which is focused on clean energy, so electric vehicle plays an important part of the state transportation. But for this trend to happen, it's going to depend on the people feeling confident that they can charge when they need to. By this, I'm talking about the range of anxiety, which is the fear of running out of battery without a nearby charger. This concern is important for people who cannot easily charge at home, such as the renters, people with a multi-family housing, or people without a private parking. So the question is not only whether New Jersey is building more chargers, the question is whether the public charging infrastructure is growing in a way that is especially fair, so that no communities are left behind. The main question I ask is whether public charging stations are evenly distributed across a state census tract or whether they are concentrated in certain socioeconomic and geographic areas. So I break this into three objectives, which first I look at the spatial distribution. For example, where are the chargers located and which places have more or less access. Then I test clustering using Moran's eye, which tells us whether nearby tracks tend to have similar charging access levels. Third, I use regression modeling to see track characteristics such as the income, poverty, no vehicle household, and population density, and see if they are associated with station counts. This is the workflow of the project, where I start by loading three datasets, which I'm going to provide more details. Then I perform data cleaning. After that, I project the spatial layers and use a spatial join to assign each station point to the census tract that contains it. Once the station counts are attached to the tracts, I build population adjusted rates such as stations for per 10,000 residents. And finally, I analyze the data using EDA or exploratory data analysis and maps, Moran's eye, and the negative binomial regression. So here are the three main datasets that I use. The first is the public electric vehicle charging station data. These are point locations, and I filter the data to be public open stations in New Jersey with valid coordinates. This station data also includes level 2 and direct current or DC fast charging ports. The second dataset is the ACS demographic data. This is going to give us the track level variables such as the population, the median income, poverty rate, no vehicle household, and owner occupancy. The third dataset is the census tract boundary file. This is going to give us the polygon geometric for all 2,181 New Jersey census tracts. The key technical step is the spatial join. Since electric vehicle stations are points and census data are polygons, I assign each station to the tract that contains it. After that, each row in the final dataset represents one census tract with demographic, station counts, port counts, rate, and spatial variables. So this is the statewide summary of our data. The analysis includes the 2,181 New Jersey census tract. After filtering the station data, there are 1,822 public open EV charging stations and 6,027 total charging ports. But the most important number on this slide is the 32.1%. Only about one-third of the New Jersey census tract contains at least one public station, one public charging station, which means that 701 tracts have a station, while 1,408 tracts have none. So even though there is a sizable public charging network statewide, the access is not evenly spread across neighborhoods. This is the first major sign that public charging access is concentrated. Before going fully into the tract level analysis, I use counties as a familiar first look. The counties with the highest stations are Bergen, and the other two I'm just going to avoid pronouncing. This is going to be followed by Hudson and Morris. And this suggests that the charging infrastructure is especially concentrated in the northern and central New Jersey. And just one more thing to keep in mind that these are the raw county counts. This is one of the most important exploratory results. The distribution of station counts is zero heavy and right skewed, as we can see mostly on the left graph, which means that most of the census tract have no public electric vehicle station, while a small number of tracts have multiple stations. The that large zero bar tells us that local station access is missing in many neighborhoods. The high count tract, on the other hand, likely represents the infrastructure for commercial areas, workplace locations, parking facilities, highway, and destination for charging sites. This pattern also matters statistically, since the outcome is a count variable and since it has many zeros and a long right tail. Ordinary linear regression will not be ideal. This is why I use negative binomial later in this analysis. On this slide, we're going to shift from raw station counts to population adjusted access. The rate is going to be stations per 10,000 residents, and this is going to be helpful because a tract with many stations may also have many people, so the rate gives an overview of access relative to the population size. The histogram shows that this rate is also right skewed. Most tracks have zero or very low station availability, while a few tracks have high rates. The map shows where those higher rates tracks appear geographically. For this map, tracks with population below 500 are excluded because a very small population can create misleading and large per capita rates. But the key point is that even after cleaning, population adjusted access remains uneven. This is going to be our descriptive equity comparison. I compare tracks with at least one public station to tracks with no station. Tracks with the station have higher median income, with about $112,000 compared with a $98,000 for tracks without a station. Poverty is also slightly lower in station tracks, with about 6.1% compared to 7.6%. So the descriptive pattern suggests that the station tracks are somewhat wealthier, but I want to be careful here. This do not necessarily prove that income cause charger placements. It shows like an association, and it tells us that demographics are worth testing in this model. So these maps are going to add spatial context around the charging patterns. The income maps help us show where higher income tracts are located. It is useful for comparison, but it should not be interpreted as proof that income directly causes station placements. The no vehicle household map is an equity context variable where areas with higher no vehicle shares may not necessarily have higher electric vehicle demand today, but they are important for thinking about transportation access more broadly. The distance map is especially important. Station counts depends on track boundaries, but drivers do not stop at the track boundaries. A track may have 0 stations inside, but still be close to a charger in a neighborhood track. So distance to the nearest charger gives a more continuous measure of accessibility, and darker blue means farther from the nearest public charger, which points to areas with weaker spatial access. To test whether charging access is spatially clustered, I use global Moran's eye. Moran's eye asks whether nearby tracks tend to have similar values. In this case, it tests whether nearby tracks tend to have similar levels of charging access. The Moran's eye value is 0.09 and the p-value is extremely small. That means that the clustering is statistically significant, but the value itself is modest. So I do not want to overstate the result. The correct interpretation is that electric vehicle charging access shows modest but statistically significant spatial clustering. In other words, charging access is not randomly scattered across the state, and nearby tracks tend to be somewhat similar to each other. For the regression analysis, I use the negative binomial model because the outcome is the number of stations in each track, and the exploratory data analysis showed that this outcome is zero heavy and over dispersed, so a negative binomial model is more appropriate than the ordinary linear regression. The model also includes the log population, and this means that the model accounts for track population size, so larger and smaller tracks are not treated the same. In the baseline, median income median income is positive and statistically significant. That means that higher income tracks are associated with higher expected station counts, holding the other variables and population constant. Owner occupancy is negative and significant, which may suggest that station placement is less concentrated in more owner-occupied residential areas. And poverty is not significant in the baseline model, and no vehicle share is also significant there. Then I add the population density. The density adjusted model improves the model fit with the AIC, dropping from 5,000 to 4,900. A lower AC means the model fits better. The population density coefficient is negative, but it needs careful interpretation. Since the population is already in the model as an offset, density is asking whether station availability per resident changes in denser areas after accounting for population and demographics. This may reflect the fact that many chargers are located in commercial, highway, workplace, or destination-oriented tracks rather than simple and dense residential tracks. After the baseline model, I look at the residuals, and the residuals show where the model predicts too many or too few stations. On this map, blue tracks have fewer stations than predicted, while red tracks have more stations than predicted. The important result is that the residuals Moran's eye is still significant. That means that the model errors are spatially clustered. In other words, the model is still missing geographic trends, and some tracks have many more stations than predicted by demographics alone. This is one of the main limitations of the model, So demographics explain part of the pattern, but the land use and transportation infrastructure likely explain more. To conclude, this project shows that public electric vehicle charging access in New Jersey is uneven across the census tract. Only about 32.1% of tracts have at least one public station. The station count's distribution is zero heavy and right skew, meaning that most tracts have no stations, while a small number contains multiple stations. Moran's eye shows a modest but statistically significant spatial clustering, so access is not randomly distributed across the space. The regression results suggest that the income is positive associated with station counts, while owner occupancy is negative as associated. The residual results show that demographics do not tell the whole story. So the biggest takeaway is that EV charging access is not only a technology issue, but also a spatial planning and equity issue. So for future work, I will add highway and interchange access, commercial land use, retail centers, employment density, parking availability, and EV adoption data, as well as the network travel time instead of the straight line distances. So this is going to be all for our project. So I hope you enjoyed this presentation as much as I did. And if you have any questions, please just write me an email. Thank you.